This toy has fascinated me since childhood. To me, its motion is almost hypnotic. Here's how it operates. Wet the bird's beak thoroughly with room temperature water. The opaque container makes it look chilled, but it isn't. Then stand it upright. It'll take a few seconds for it to start drinking. Notice that all of the action right now takes place in the stem here. As I speed up the action, you see liquid rising and the bird rocking back and forth. If I return to normal speed, you can see the bird slowly, very, very slowly, rock forward until it takes a drink, which it will do again and again. In this video, I'll detail the bird's clever engineering design, explain how it uses thermodynamics, and link its action to some of the greatest and most impactful devices created by engineers. This toy has a long history, but its current incarnation is due to Miles V. Sullivan, a scientist at Bell Labs. He specialized in methods of manufacturing semiconductors, but as a sideline invented toys. It's reported that this bird delighted U.S. President Herbert Hoover, an engineer who failed to figure out how it worked, and it also defeated the great scientist Albert Einstein, who spent 3.5 months studying it. It's reported that he refused to take the bird apart. With the benefit of hindsight, let's start by exploring how it works and examining the key engineering design aspects. First, let's ask, is the water ornamental or essential? At first, the bird acts just as if the water were still there. Now let's speed up the motion. You see at 15 minutes it's still drinking, at 30 minutes still drinking, 45 minutes still drinking, 60 minutes still drinking, 75 minutes still drinking, and 5 or 10 minutes later, at 8 or 85 minutes, it takes its last drink. The liquid still rises a bit, but it never rises enough to make the bird tip over, which shows that the motion is not perpetual. As long as there's water, the bird keeps drinking. Let's look inside the bird to get an idea of how it works. Underneath the bird's hat, beak, and fabric covering lies a glass bulb, smaller than the bulb at the base and also rounder. Now, watch as I put a few drops of isopropyl alcohol on the top bulb to cool it. The liquid rapidly rises to the head. This changes the bird's center of gravity so that it will tilt forward. The head now fills with liquid, and then, there, it drinks. It becomes upright, and the liquid drains from the head. Liquid rises again to the head, and the bird drinks again. This cycle repeats until all of the isopropyl alcohol on the bird's head evaporates. Why does the liquid rise? The place to begin is with the bird's manufacture. The bird is filled through this tap, a small pipe built into the head with methylene chloride dyed red, which is then frozen, a vacuum applied to evacuate the air, the tap sealed, and of course later hidden by the bird's hat. And then the methylene chloride melts. It turns to liquid, and then some of it evaporates, turns into vapor. The key to the bird's operation is that the vapor in the head and in the base are separated by the liquid in the base. It's hard to see, but a tube extends into the base, nearly reaching the bottom. This separates the vapor in the base and the vapor in the tube and, of course, the head. So at rest, the pressure in these two spaces are equal, but when the bird's beak is wet, the temperature falls, and as I'll explain in a moment, the pressure in the head drops below that in the base and the liquid rises. Of course, this liquid in the head causes the bird to tilt forward to drink, and when it drinks, the vapor in the head and the base are connected. The pressures nearly equalize. A slug of vapor rises to the top, and some liquid drains from the head, and then the cycle repeats. To see the pressure equalize, I'll slow down the bird as I tilt it forward. Right now the head is half full. When I tilt it, you see a slug of vapor go from bottom to top. I've tilted it far enough forward that the liquid in the head is below the top of the tube, and the liquid in the base is below the section of the tube that almost reaches the bottom of the bird. This allows the pressure to equalize, and as the bird becomes upright, the liquid returns to the base before the cycle starts again. In operation, it doesn't tilt quite this far forward, and so the pressures don't fully equalize. Why, though, does the pressure in the head drop as the temperature falls? You can see the answer if I shoot cool, compressed gas across the bird's head. As the cool gas strikes, you see liquid condensing inside the head. And, as you see on the left, this causes the liquid in the base to rise. The cool gas withdraws energy as heat from the head, causing some of the methylene chloride vapor inside to condense to turn into a liquid. This decreases dramatically the amount of vapor in the head. Liquid is 1,000 times more dense than vapor. This in turn lowers the pressure in the head and causes the liquid to rise. I used compressed gas to cool the head because I can control the amount of cooling. The bird, though, cools its head by drinking. The head is wrapped in fabric that absorbs water. As I put drops on its beak, you can see the water beads up at first, then saturates the fabric and spreads rapidly across the bird's face. On the right side, you can see it creeping to the back of the head. If I now turn the bird around, you can see that the water has spread to the back. As I continue adding drops on the beak, the saturated area on the back increases. When this water evaporates into the air, it removes energy from the bulb as heat. You feel this effect every time you step out of the shower. The evaporating water withdraws energy as heat and chills you. This evaporation, this withdrawal of heat, lowers the temperature and begins the condensation of the vapor, which starts the cycle, as I showed you with a cool, compressed gas. As long as the head is wet and heat is withdrawn from it, the bird will always drink. But if you were to operate the bird in humid air, it would slow down because little water would evaporate. And if the air were at 100% humidity, the bird would stop because no water would evaporate at all. Now, to make this dramatic condensation happen, when the temperature is lowered just slightly, the evaporating water lowers the temperature by about 0.3 of a degree, the bird's designer chose a highly volatile liquid. This means one whose boiling point is near ambient temperature because for small changes in temperature, there's a large change from vapor to liquid, and so the variation of pressure is large. Watch what happens as I heat the base of the bird with my hand. You see the liquid level in the base dropping. That's because energy from my hand is converting some of the liquid into vapor, which increases the pressure in this region. And that causes the liquid to rise to the head. Eventually, I heat the vapor so much that it shoots up the stem. Now, watch as I place my hand around the head. Heat from my hand converts liquid to vapor, which increases the pressure and forces the liquid back to the base. To test this explanation of the bird's operation, let's activate the bird in different ways. As I noted, it is the temperature difference between its top and bottom that drives liquid to rise to the head. So let's see what happens if I point a light at the base of the bird, which I've painted black so it will absorb the energy from the light better. As I heat the base of the bird, the liquid rises as before, but the bird tips backwards. The wet nose tilted the center of gravity, and so I've added some modeling clay to the nose to get the bird to tilt forward. And now, when I turn on the light, the liquid rises. The bird drinks just as if there were liquid in front of it until I turn the light off, and the bird drinks for a little bit longer until eventually it comes to rest. Next, let's see what happens if we use this whiskey. Again, thoroughly wet the bird's beak with the liquid. Stand it upright, and then we see again the liquid rising in the bird. And then it drinks. We can also now understand why the bird's rate of drinking differs among the three methods I use to activate the bird: a heat lamp, whiskey, and water. Roughly, the heat bird takes 3 drinks for every one of the water bird. The whiskey bird takes 2 for every drink of the water bird. The reason the bird drinks whiskey faster than water is because the rate of evaporation of the alcohol is greater than that of water. This means that heat is withdrawn faster from the head, and so more vapor condenses in a shorter amount of time, which accelerates the pressure difference. The heat lamp causes the greatest difference of all, which highlights how an engineer thinks about this bird. To an engineer, this bird is a heat engine. A heat engine turns heat differences into work, mechanical motion. To see that, recall that when the bird is just about to drink, that its head is at a lower temperature than its base, which is at ambient temperature. Then, when it drinks, the pressure in the head and base start to equalize, so liquid returns to the base, but the overall temperature of the bird is now just a little below ambient temperature. When it returns to upright, the base draws in energy as heat. The head then rejects some energy as heat, and the bird drinks again. These 2 flows define a heat engine, a device operating in a cycle that absorbs heat from a high-temperature reservoir, converts part of it into work, and rejects the remainder into a low-temperature reservoir. The fact that it's a heat engine means it's related to the great machines that make our globalized world happen. Among those, the mighty steam turbine that generates electricity, the giant diesel engine that propels container ships across the oceans, and the great gas turbine that flies us around the globe. I'm Bill Hammack, the Engineer Guy.